are going to look at Equilibria, but with the eye of how can I use it to investigate quantitatively what's going on with the sample. And the big application here is precipitation, particularly fractional precipitation, where we'll take a mixture of solutions and then precipitate them one at a time from each other. The lab that met this morning, well, you were in lab, they did a separation of a mixture by precipitations. But that would not count as being a fractional precipitation, because every time they made a precipitate, they then changed the reagents. We would count it as being a fractional precipitation if we used one reagent and it precipitated ions out of solution in a sequence. Okay? So let's have a quick revisit of Equilibria so that we've got all the terms down. We know what we're going to be talking about. This is a couple of things that we're going to lean on and just assume that we know. And these were topics out of Chemistry 2 that were here's the topic and there's this. This is now the thing that we're going to be building off. Okay. So, I have 4 species in solution, all at the same time. A and B are reactants and they form C and D. That arrow is the equilibrium arrow that tells us that the concentrations or the progress of this reaction is not total. It is set, but it's not total. All of A and B did not turn into exclusively C and D, but in solution all 4 of those exist. And if we did this in the gas phase, we won't be doing gas reactions, but if we did it in the gas phase, then all 4 of those gases would exist. And if we're going to do things that have dissolved ions and gases and solids, then we would do a combination. All right. This equilibrium is dynamic. What that means is that things are flowing, but the value is fixed. The position is set. When I say fixed, we can move it, but it has reached a point. So at equilibrium, the balance of A and B being turned into C and D has come to some natural point that we call equilibrium. If I were to take any additional B and A and turn them into C and D, then some C and Ds would have to turn back into A's and B's. So this is in constant flux. It is moving backwards and forwards, but settling on a point of balance. So equilibrium is a dynamic phenomenon. Okay, the position of equilibrium quantitatively can be determined as the equilibrium constant. And it is a number that tells us how far to the right, product side, or how far to the left, reactant side, this balance is. When we say balance, it doesn't mean right down the middle. The equilibrium position can be very, very heavily to the right or very heavily to the left. But it's the point at which any further reactant that turns into product, some product has to be exchanged back for reactant. Okay. Do we remember what goes into this?
Concentration of power supply.
Yeah, yeah. But there's something, we'll write that down let's write it now. We'll write that down now and then see if we can backtrack to get to what it means. So this is the ratio of the concentration of products. This could be a pressure. If we determine something, its value in terms of pressure, this then becomes a Kp. If we determine it in terms of concentration, it becomes a Kc. Okay, so because I've expressed that in terms of concentration, this is now a Kc. And it is products over reactants, which tells us progression. That as this number gets larger, that means we have more products. And because all of the products came from reactants, as this number gets larger, it is pulling numbers out of this basket. And so that number gets bigger, this number gets smaller, the value of K gets progressively doubly big, right? Because you've now got two factors. When I say doubly, I don't mean actually 2 times, but more big. Because I'm making that number bigger and making that number smaller. I'm having the effect twice. Okay. So for us, this is the concentration of A divided by the concentration of B. Nope. A and B are not products. C and D are products, and A and B are reactants. Okay. Anything else we need to worry about? No, not right now. If this is 1 to 1 to 1 to 1, then this is what it is. But if I have 2 of those reacting with 3 of those, making 8 of these and 1 of those, I have coefficients in there, then I need to raise all of my concentrations to those powers. Outside of the chapter on equilibrium, chapters, there were 3 of them in chemistry 2, where else did we see concentrations being multiplied by each other raised to a power? Because this is the actual key to what the value of K means.
Can you ask that one more time?
Yes. Which other chapter in the textbook for chemistry 2 did we see concentrations of
Solubility.
reactants being raised to a power?
Solubility. Is that?
What did we learn? Our chapters were solubility, kinetics, equilibrium, changes in equilibrium, then thermodynamics, delta G, and nuclear chemistry.
What?
We did nuclear chemistry too, right? Did we do radioisotopes at the end?
Yes.
Mhm.
Oh,
Which one of those chapters had concentrations raised to a power?
yeah. Was it kinetics?
Kinetics. Because, what if this wasn't an equilibrium, but this was a reaction? How would you describe its rate? Because we can describe rate three ways: with a rate expression, a rate law, or a rate equation. We could write the rate law that says rate equals K times the concentration of the reactants. The rate of a reaction only depends on the concentration of its reactants. And then, when you say it depends on the concentration of the reactants, it might not. It could be zero order, first order, second order. Those are determined here by, if it's a fundamental process, we get to write those. If not, we don't know. So that would be the rate forward. And my K, this is a lowercase k. The equilibrium constant is an uppercase K. What if this fraction's been written the wrong way around? The rate of reaction can only be dependent on the reactants, because it's only the reactants that are doing the reacting. The products aren't reacting. The products have been made, or have not been made yet. At equilibrium, the rate forward and the rate backwards are the same as each other.
God's sake, sorry.
I know, yeah. I know, so that kind of dodged our attention. The K is just that. It's the rate forward divided by the rate backwards. Oh, I didn't put my, it's already gone. Didn't put my little coefficients in for that bottom one, but I think we know what to do. All right, so that's what equilibrium is. If only it were that simple, because then there were a whole lot of complications that revolved around two things. Okay, let's throw a couple of things up on the board. Here's a nitrogen. The book loves this one. This is the Haber-Bosch process. It's really, really important. these are all gases. These are all in the gas phase. The nitrogen gas and hydrogen gas come together to make ammonia gas. And that doesn't balance. We need 3 hydrogens to make 6 hydrogen atoms, 3 hydrogen molecules to react with the 2 nitrogen atoms in the nitrogen molecule to make 2 molecules of ammonia. Okay. So the K for this gets to be the concentration of that squared divided by the concentration of this multiplied by the concentration of that cubed. Or, if we are going to measure these in gases as pressure, that this would be the partial pressure of the ammonia squared divided by the pressure of the nitrogen multiplied by the pressure of the hydrogen cubed.
Quick question.
Yeah.
So why would the ammonia go on the top? How do you know?
Because it's written that way.
Okay.
Because it's written left to right. If I said, this is in equilibrium, and it absolutely is in equilibrium,
Mm-hmm.
because we've already established it's in equilibrium. Then this K, if we write it as a concentration, is N2 over H2 cubed over NH3 squared.
Oh.
Okay. This is the reverse of that. So if we called this 1, reaction 1, this would be minus 1, because they're going in the opposite way, they're going in the opposite directions. And because this one is upside down, in comparison to that one, the value of Kc1 is equal to 1 over the value of Kc minus 1. They're the reciprocal of each other. So if you're given a question that asks you, tell me about this equilibrium, but the book lists the equilibrium this way, and it gives you the value of the equilibrium constants, just take the reciprocal of it, because it's the reverse. And when the reaction is reversed, then the number is inversed. It's turned upside down. Yeah, it's a good timely question. Okay. This, products divided by reactants. This is products divided by reactants. So Kc is equal to Kp then?
No.
No, it isn't. It wasn't. It wasn't. There was an adjustment that we have to make.
Mm.
What was that adjustment? Go find it. There's R.
Oh yeah. Kp equals Kc times RT to the change in N.
Let's write it the other way. The Kp equals Kc, these are uppercase Ks, multiplied by
RT.
R is the universal gas constant. T is
Temperature.
temperature.
Mm.
And then,
Delta N, which is change in moles.
like this, So what is the delta N? How much of this is the delta N changing? The T or the RT or all
RT.
of it? Yeah. There you go. That's correct. Okay, so one of the things, fun things that we will figure out this term is that R, the constant, is allowed to have many, many, many different values. That it can still be a constant, but it will have different values depending on what you ask. Okay. Let's have a look at that, because R is really cool. Somebody pointed this out to me about a year, maybe a year and a half ago, and I've never looked at it quite the same way since. PV equals nRT, right? Ideal gas equation. That the pressure multiplied by the volume is equal to the number of moles times this value R that we look up in a book times the temperature. And of course, the thing about temperature is every time it's in a math equation, it's in Kelvin. Because Kelvin doesn't go negative, and we can't have negative numbers pop up into things that have outcomes in the world of either volume or in the world of energy, because those negatives become meaningful. All right, let's isolate R. If PV equals nRT, then R is PV over NT. This is the way that they should write the equation in the textbook. I've completely changed my opinion on this, because what this tells us is that number contains all the information you will ever need to know about the pressure, volume, molar temperature relationship for that gas. It is the number that is holding everything down. And if that pressure is in atmospheres and this volume is in liters, then we use the value of R equals 0.0821 liter atmospheres per mole per Kelvin. Moles are always going to be in moles. Temperature's pretty much always going to be in Kelvin. I can't imagine anybody has made this work in a temperature scale that's not Kelvin. But pressure's not always in atmospheres. Are atmospheres the SI unit for pressure? No, they are not. What is? Pascals are. And how many pascals are in an atmosphere?
That's not the 101.
It's 101,325.
That sounds right.
It's an ungainly number. Atmospheres work for general chemistry because an atmosphere is this, what you're experiencing. It's easy to understand. The numbers make sense. But it's not the numbers that we've decided on globally as a science community that we're going to use. We've said we'd use pascals. It could be that we do that in pascals or kilopascals or in torr or in millimeters of mercury or in bars. Anybody seen bars? Bars is lowercase. It's not a capital B. It's a lowercase b, I think. You know what a bar is?
No. Do we get
Bars and atmospheres are similar to each other, but what they've done is they've settled on a number that is better matched with another number. And it's not, when I'm writing on the board in a minute, I'll tell you what it is. The bar is very, very similar to an atmosphere, but it's different. Millimeters of mercury are from barometry, meteorological measurement of pressure. 760 millimeters of mercury is 1 atmosphere. Who knows what the conversion from a millimeter of mercury to a Pascal is? But it could be, we won't be using PSI, pounds per square inch, or anything silly like that. And volume, what's the SI unit for volume? Is it a litre? No. No, a cubic centimetre would be a milliliter, which is useful. Litres are really useful.
Is it DCM? Deciliter?
So a cubic deciliter, I think, is also a litre. Because it's 10 times 10, divided 10th and 10th. 10 and 10 and 10 is 1,000. So your conversion factor works. No, it's cubic meter.
Oh, I forgot. Oops.
SI unit for volume is a cubic meter. So when we go look up the value of R, we'll find that Pascal's cubic meters is not this number. It often turns out to be 8.3144 something.
Oh, yeah, the R value.
Okay. So, a couple of wrinkles. This is not equal to that. It has an adjustment factor, and the adjustment factor contains a very interesting number, R. This right here, this has to be stated because we don't know what delta N is. Delta N is the difference in the number of moles of
Like the products to reactants.
products minus reactants. Because gases respond to temperature more than solids or liquids do, solutions do. They have a bigger effect on volume than solutions do. So we have to keep track of which side of my equilibrium contains the most number of gases. Okay. Which side of the equilibrium contains the most number of gases? So there's additional stuff hiding here. It surfaces here when we try to make sense of the numbers. And this is the first time that it says, you're really going to need to take into account which way you are trying to push this equilibrium, this reaction. On this side, I have 4 gas moles. and on that side, I have 2 gas moles. Tell me anything at all about this reaction.
It's not as easy to go to the right as it is to the left because you're decreasing entropy.
Entropy. Sounds like entropy is in here somewhere. Entropy is the amount of disorder. And this reaction is not favored entropically. There are 2 factors that determine whether a reaction goes in the direction shown. They are enthalpy, which is the dominant factor. It's several hundred times larger than entropy, which is the disorder. Gases have very, very high entropy, much, much higher than liquid solutions or solids. Solids have very low entropy. And so the side that has the most number of gases is the side that nature probably is leaning towards. Now, enthalpy is going to overrule that, given a chance. But we really need to take that into consideration. Okay, so we have 2 things. Whether a reaction goes this way or that way was determined by a thermodynamic value. Whose thermodynamic value? Somebody put their name to it.
Oh my gosh, it's there.
Thermodynamic value.
Mm.
Wait, yeah. Gibbs.
Oh,
Gibbs free energy says yes or no. Yes, the reaction that you have written down will go in the direction that you have proposed, or no, that reaction will not go in the direction you have proposed, it will go in the opposite direction.
Dr. Bar, is this the one where it was like enthalpy plus entropy times temperature? Is that a different one?
No, that's right.
Delta G equals delta H minus T delta S. There are 2 thermodynamic factors involved. Technically 3 if you include temperature. Enthalpy. Enthalpies are usually in kilojoules, thousands of joules. Entropies are usually in joules, maybe hundreds of joules. So this number is probably hundreds of times smaller than that number. But the temperature, because it's in Kelvin, is a value that's in the hundreds. And so now we get this toss-up of does this value overrule that value? Okay. Tell me everything I need to know about enthalpy in 1 sentence, maybe 2. What do its values look like? Positive or negative? Which ones are most likely to go that way? Positive or negative? Negative. So, negative, I'm going to write VE, that means negative. Negative delta H is exothermic, gives out heat, which means that your reactants were higher in energy than your products are. Means your products are stable. If your products are stable, then the reaction is more likely to go this way. Entropy. If we want the reaction to go this way, do we want entropy to be positive or negative?
Positive.
Okay. So reactions that have combinations of negative enthalpies and positive entropies go that way. When this is a big negative number, and I subtract a number from it, it goes more negative. If this was negative, and I subtract a negative number from it, this number would become less negative, up to the point where it no longer goes forward. So, if delta G is a value below 0, meaning it is negative, then the reaction is spontaneous in this direction. If delta G is a positive value, then the reaction is spontaneous in the reverse direction. The reverse direction to the one that you have shown. At equilibrium, is the reaction going forward to the left or to the right, or going back to the left? What's happening at equilibrium? Is it going left to right or right to left?
Both.
It's both, evenly. So at equilibrium, delta G is not a negative number and is not a positive number. At equilibrium, delta G is 0. At equilibrium, delta G equals minus RT ln K. Ln is the natural log. K is our value of the equilibrium constant. T is our temperature in Kelvin. And R is the universal gas constant. But this time, this is an energy. It's in joules. So this gets to be the 8.3144 joules. We usually write the Kelvin first. Joules per Kelvin per mole. 8.3144. It's the same number, just imagined a different way. Okay. So we have equilibrium. We know that we can find a number from concentrations or pressures. That if I find a number using pressure and I want to use it in going forward in a calculation using concentration, I have to change those numbers. I know that it is rooted in kinetics, but it's also rooted in thermodynamics. It's where everything's meeting together. Okay. There's a couple of other things that we have to remember. Here's a reaction that is in equilibrium. Calcium carbonate reactant generates calcium oxide and carbon dioxide gas as products. So the K is concentration of products divided by concentration of reactants, which goes to be, here's my calcium oxide, there's my carbon dioxide. There are no coefficients here, so nothing has to be raised to any power. And I'm going to divide that by the calcium carbonate. All good?
Wait,
Wait.
the solids can't be in concentration?
Solids can't have concentrations because solids have their own definite volume. So these get removed. And the K for this is just that. So what we have to do is we have to remove solids and liquids. From the K expression. K expression is this thing. So when you're writing this out and you know that you're going to do it wrong, you can give this one a check mark that just tells the reader, I'm not 100% committed to my answer here. That this is my preliminary answer. It contains two things that I'm going to remove later because solids cannot have concentration. Solutions have concentration. Gases have concentration. Solids and liquids don't. Okay. All right. And then you've got the Chatelier's principle that said what?
Like, whatever you do to one side, you do. Well,
It says everything is hopeless. Anything you do to an equilibrium, it will counteract. That equilibria exist for some reason. That reason would now appear to be pinned in thermodynamics. That there is a reason that is your position. And when you make an external change, nature fights back and counteracts that change. So, external influences to equilibria will be counteracted. Okay. Give me an example.
whenever you increase or whenever you change volume, you decrease or increase pressure.
Okay.
They're inverse of each other.
Okay, so PV equals nRT, which means that P is nRT over V. Volume and pressure have an inverse relationship. That if I had a system the gases, be they reactants and products, are all occupying this space. When I allow those to escape into a larger volume, I've made a change. And the equilibrium position might change to take care of that. This one, it depends. Let's go back to the one that we've already used a couple of times, just because it's easy. These are all gases. There are 4 here and 2 there. 4 gas moles, 2 gas moles. All right, let's ask the question in reverse. The gas is in this container. The container is a piston, so I can change its volume. It has settled at equilibrium, where the nitrogens and hydrogens have turned into ammonias, and every new ammonia that is made, some ammonia turns back into nitrogen and hydrogen. When I reduce the volume and squeeze the gas down tight, what happens to my equilibrium position?
It'll shift more towards the right.
Because,
That side has less amount
Yeah.
of atoms.
yeah. So, decreasing volume increases pressure, the total pressure. And that favors the side with the least amount of gas particles. Because the gas moles are sensitive to pressure. And the more of them that you have, the more sensitive they are. So when we decrease the volume, we increase the pressure, we will push, and our equilibrium position shifts that way. I can't remember. I think this reaction is exothermic. I'm going to just do a quick check. This is called the Haber-Bosch. Haber, Bosch. I think it's exothermic.
Yeah.
Yeah. So, don't need to know the value, but delta H here is negative. It's exothermic. Here's something that we can do. If this reaction is exothermic, is heat a reactant or a product? It's a product. So as this reaction progresses, it gives out heat, it's exothermic. So here's a question. What happens to the equilibrium position if the reaction is heated? heating the reaction is my external influence.
That'll hinder it, right? So also with this heating, you're adding heat.
Heat is already here. It's already as a product. So when I add additional heat, now I have too much heat. I have too many products. These count as products. So I have too many products.
More react.
Yeah. And my reaction shifts this way. This will convert products back into being reactants. Counteracts what you're trying to do. Okay. Let's think. I'm sure I can have chosen a better one than cobalt, but we'll use the cobalt one. All nitrates are soluble. All ammonium salts are soluble. All sodium salts are soluble. All potassium salts are soluble. Most chlorides are soluble. Most sulfates are soluble. Most hydroxides are insoluble. The fact that we have sodium hydroxide as a base is thanks to it being a sodium salt, not thanks to it being a hydroxide. Most hydroxides are insoluble. So here's cobalt hydroxide, and it is only slightly soluble in water. And we would write that equilibrium something like this. Here is cobalt hydroxide. And we can write the water in on this side if we want to. It's going to make no difference in the end. And it goes to being aqueous cobalt hydroxide. Okay. Now, because cobalt hydroxide is from the ionic world, the metal, and a non-metal, what this means is cobalt 2+ and 2 hydroxides. Because we've agreed that anything ionic, when it's in solution, splits apart as its ions. So this middleman right here, not needed. It's just for explanation. Okay, when you write the value of K, the products are the cobalt ion and the hydroxide ion squared, because there's 2 of them, divided by, these are AQs, aqueous solutions, divided by my original cobalt hydroxide, which is a solid, and multiply that by the concentration of the liquid water. But Liquids don't have concentration. Solutions do. Solids don't have concentration. Solutions do. So this is a K that is specifically for soluble species, and it's called SP. It's the solubility product. Just means multiply the ions by themselves. Product. Take two numbers and multiply them by each other. Okay. That's my solubility product for cobalt hydroxide. Here's my final question. What happens to the solubility of cobalt hydroxide when your pH increases?
The solubility increases.
Let's break this down. pH is a scale from 14 to 0 with 7 in the middle. This is where the bases are, and this is where the acid is. So when I make the solution have a higher pH, at 7, the amount of H plus in solution is equal to the amount of hydroxide. At low numbers, the amount of acid, H plus, is larger than the number of hydroxide. And at high pH, the concentration of H plus is less than the value of hydroxide. So, at high pH, that means hydroxide concentration just went up, been added. I'm going to change. This is my external influence. So I have my equilibrium, and I'm adding additional hydroxide. Equilibrium position is going to change that way. And the outcome is this becomes less soluble. That's what we're going to use to our advantage, to one by one pull ions out of solution. The simplest way is to change its pH, or find an anion that is insoluble with some particular ions. Okay, we'll do that next week. Yeah. See you then.